This is a continuation of my series about where I solve problems that involve finding invariants in real time. I'm still hoping that I'll get, in some sense, better at these, but I don't really mean better in the sense of um, I'm not quite sure what I mean. I want to get better in the sense of becoming more systematic about them somehow. So, but I don't really feel as though that's happening yet. But on the other hand, I'm only on exercise 15 out of 60, so perhaps that will come in due course. Perhaps I am unconsciously slightly more systematic, but we'll see. I've got to find my writing program. Yes, I've got that, and that's something else. And so I'm going to just to remind you, or show if you haven't seen, I'm taking problems out of the first chapter of this book, and the next problem that I've not done is number 16, and that says each term in a sequence one naught, one naught, one naught, one naught. It's odd that it doesn't say the sequence, but perhaps that's we'll understand why in a moment. Oh, starting with the seventh. Is this going to be some Fibonacci generalization or something? Is the sum of the last 6 terms mod 10? Okay. What on earth could they be going to ask? Prove that the sequence 0, 1, 0, 1, 0, 1 never occurs. I take it that means as a subsequence of this sequence. Okay, well, we could just do something disgusting and just keep going until it starts repeating, which it'll have to do eventually. But there must be a better way. But I think I will just again, there's this tension between should I stop and actually think, or should I not bother thinking just for the moment and just see what happens. So I'm going to try not thinking for a bit. So I'm going to add up everything mod 10 and I'll get 3 here. Now I add up those lots, mod 1, 2, 3, 4, 5, 6. I get 1 plus 1 plus 3, which is 5. Now I get 5, 8, 9, 10. So that's 0. Now I get 8, 9. And now I get 9, 4, 7, 8. Hope I'm not making any mistakes here. Now I get 8, 7, 2, 5. And I'm going to stop there because it's just some randomish looking sequence. It's going to take me ages even to sort of threaten to get 0, 1, 0, 1, 0, 1. So now I need to think about what could possibly be preserved. And I think what I want to do is to have some function of subsequences of length 6 that gets preserved, because we can have 1, 0, 1, 0, 1, 0, because we've started with 1, 0, 1, 0, 1, 0. So what could be different about that and 0, 1, 0, 1, 0, 1? So for example, summing the digits in some sense is not going to distinguish between those two, but maybe some kind of alternating sum or something like that. So, but what happens when I remove this 1 and I add this 3? So my immediate reaction to this is having no idea what to do. But I would really quite like an invariant. So if I wanted an invariant, I think maybe I will try to be systematic. So supposing I got a subsequence of the form A1, A2, up to A6. Supposing I look at a combination of the form. So this is a bit of a guess, but what I'm doing, I'm trying to be systematic by just saying, let's write down a whole class of potential invariants, and we'll see if any of them works. So I'm going to look at an invariant of the form A1N1 plus A2N2 plus A6N6. Now if I want that to be an invariant, what I'm going to need is that equals A2N1, I'm now going to replace this sequence by A2 up to A6 and A1 plus up to A6. So the next term is the sum of the previous ones. And all this is mod 10. So if I'm going to say that everything I'm writing down should be interpreted mod 10. So these ni's are mod 10 and everything. So that should equal A2N1 plus A3N2 plus A6N5 plus A1 all the way up to A6N6. And if we want that to be an invariant, we sort of would ideally like that to be the case for all A1 up to A6. And that's going to give us a whole lot of rather stringent conditions, I think. So, for example, we're going to have that. Is that even possible, though? Let's just compare coefficients of A1. So by comparing coefficients of A1, we'll get that N1 here should equal N6. And by comparing coefficients of A2, we'll get that N2 equals N1 plus N6. And then N3 is going to have to be N2 plus N6, I believe. A3, N3, and then it's A3, N2 plus A3, N6, and so on. So N4 equals N3 plus N6, and N5 equals N4 plus N6. And I think I'm going to... And comparing coefficients of A6 gives me... It really does give me N6 equals N5 plus N6. So N5 equals 0, which means that N4 equals minus N6. Making some progress here, which means that N3, if N4 is minus N6, then N3 is going to be minus 2N6, and therefore N2 will be minus 3N6, and N1 will be minus 4N6. So minus 4N6 has to equal N6. So 5N6 equals 0, and it would be a rather boring invariant if N6 is 0, but remember we're mod 10, so let's take N6 to be 2 and see what happens. So I'm going to have N1 equals 2, because that's minus 4N6 mod 10. n2 will be 4, n3 will be 6, n4 will be 8, n5 will be 0, and that's n6 equals n1 equals 2. So my invariant then is, let's just write it down then, 2a1 plus 4a2 plus 6a3 plus 8a4 plus 10a5. Sorry, try to leave out, plus 2a6 mod 10. And now I'm just going to have to hope this works. So for the initial sequence, what do I get? I get 2 plus, that's a1, a3, a5. I get 2 plus 6. So I get 8 to start with. And now I'm begging for that not to be the same as what I get if I take these three. So that's, now I have 4 of those plus 8 of those plus 2. 4 plus 8 plus 2, 6 plus 8, which is 4. And I think I've solved the problem. Let's just check that again. Because I'm a little bit anxious, I'm going to write these numbers above. So 2, 4, 6, 8, 0, 2. Right, let's add that up. I get 2 plus 6 is 8. And here I have 2, 4, 6, 8, 0, 2. I get 2 plus 8 plus 4 is 4 mod 10. That really does seem to work. I suppose the other thing, if I was going to be really careful, would be to check that this was an invariant, but I don't really see how I could have got that wrong because they were rather easy equations to solve, and I solved them. So I'm going to hope that I got that right. I think I did, and move on to the next question, which is question 17. So I'm actually rather pleased about that one because I felt I was systematic. As I said, I'd thought about a class of invariants that seemed very, very likely to be the class from which the right invariant would be chosen. I couldn't just write down the right invariant, but I could work it out quite easily. So the next question, 17. Starting with any 35 integers. I like this something. This is. I always find it amusing with these questions that that rather kind of weirdly unnatural numbers like 35 come up. You may select 23 of them, so let's get better and better. Clearly there's going to be a special case of something more general, but let's not worry about that. And add 1 to each. This seems familiar. I mean, it's similar to some other question. By repeating this step, one can make all all 35 integers equal. Now it says, prove this. And that's not the end of the question. Now replace 35 and 23. Oh, so it is going to ask for something more general. By m and n, respectively. And that respectively amuses me as well, because without lots of generality, we could swap them around. What condition... This is an obvious follow-up question here. So, what condition must m and n satisfy to make the equalization possible? It's tempting to think about the second question first and specialize to 35 and 23, but maybe I'll do it the way it says. So what might I try to do that would improve the situation? So a fairly obvious strategy is to take the 23 smallest and add 1 to all of them, and then just iterate that. I might just try that with 3 and 2, because I really can't write out 35 integers. So if I had 4, 7, 12 or something like that, then I'd go to 5, 8, 6, 9, 7, 10, 8, 11, 9, 12. Now, in the case of equality, I just have to pick one at arbitrarily, so 10, 13. Now I'll go for 11, 13, and I'm getting potentially into trouble, but maybe not. So 12, 14, 13, I am in trouble. Maybe not, no, 13, 14, because before I had 12, 11, 13, and now I've got 13, 14, so this is actually looking good, and giving me a clue, I think. So 14, 15, 15, 15, and it's caught up. So that strategy looks rather promising. So what I would like to argue is that something goes down as I apply that strategy. Could it be something as simple as the maximum minus the minimum? I don't think that is necessarily... Oh, wait. So let's suppose I've got numbers A1 up to AN, and then let's suppose they're in non-decreasing order. So I've got A1 like that, and suppose I add, so I am looking at the general case M and N for the time being. So now let's suppose I replace that by A1 plus M. Sorry, A1 plus 1, A2 plus 1, up to AM plus 1, and then AM plus 1 in the other sense, up to AN. Now the maximum minus the minimum could have changed. So one of two things happens. Either the maximum minus the minimum doesn't change. Sorry, either it goes down. So if AM is less than AN, then when I add 1 here, I don't change the maximum, and so therefore the difference between the maximum and the minimum goes down by 1. Then I mean that my hoped for invariant does go down. But if AM equals AN, then max minus min stays the same. But could something nevertheless improve if I'm a little bit more careful? For example, could I argue that the number of times that the number of what I'm trying to say, something like the number of maximum elements goes down in that case? What am I trying to say? Yeah, so maybe I could argue that if the max minus the min stays the same, then I'd like the number of maximal elements to go down. Does that happen? I think it does, because if I've got A1 less than or equal to less than A R equals dot 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 equals an, and if m is greater than r, then the number of maximal elements here was, let's call that n r plus 1, just for, so the number of maximal elements here was n minus r, but if m is greater than if m is greater than r, in other words it's at least r plus 1, then it's going to be sort of here somewhere. Then when I add 1 to the first m elements, then all these ones between r plus 1 and m will add 1 and become the new maximal elements. Those will stop being maximal elements. So the number of maximal elements will have gone down from n minus r to m minus r. So we have a sort of double induction type thing going on. So notice that when that happens, the max minus the min does not go back up again. So I've definitely got something that's seemingly going down, but now it looks as though the equalization is always possible, but I don't believe that's going to be the case. I'd sort of assumed they'd have to be co-prime or something like that, but maybe that's just nonsense. I'll come back and check whether that's a proof in a moment, but let's just quickly test by looking at, say, a case where we've got 4. So let's look at that. No, let's just start with something like 1, 2, 3, 4. Then I'll get 2, 3, 3, 4, 3. I'll add to this one, so 3, 3, 4, 4, and then we get 4, 4, 4, 4. So that seemed to work quite nicely. But there could be a parity problem there. We're always going to add, if we do that, an even number. So if I'd started with 1, 2, 3, 5 or something like that, then how am I going to make them equal? Of course, the sum is odd, and I'm always going to change by and now it's sorry, now I seem to have a proof that you're never going to be able to do it, which is bizarre. So for example, it looks to me, going back to the original question, that if you select 23 of them and add 1 to each, then the sum does not change mod 23. Oh, but that's okay. We can so it does have to be co-prime, yes, because if I've got 35 integers, then if they're all the same, then when I add up together, I've got a multiple of 35. So I need a multiple of 35 to be able to be any required value mod 23. And that I can do because 35 and 23 are co-prime. So my guess that they should be co-prime is correct. So let me just quickly say exactly why that is. So if m and n does not equal, if they're not co-prime, then sum is constant mod n, mod m that is. So if it starts not a multiple of m, it cannot become one. So we can't, since n, well, let's say it starts not sorry, if it starts prefer to say this, if it starts co-prime to n, it's better. It cannot stop being co-prime. Since any multiple of n has a factor in common, with m we can't get equality of all the numbers that we're talking about. So now let's go back to what looked like a proof and try to understand why it's not necessarily a proof, but should become a proof if the numbers are co-prime. So what was the argument? We said that the max minus the min, either it decreases or it stays the same, but the number of maximal elements goes down. But is that true if the number of maximal elements is 1, for example? But that's not. That's not. Okay, let's just try to understand, going back to this 1, 2, 3, 5 example, let's just quickly understand what is going wrong with that algorithm, which we know it must go wrong, but 1, 2, 3, 5, 2, 3, 3, 5. I'm going to add 1 to those two just to keep them in increasing order. So I get 3, 3, 4, 5. And now I'll add 1 to those two, so 3, 4, 5, 5. And now I'll add 2 to those two, so 1 to those two, 4, 5, 5, 5. And now I'll add 1 to those two, and I'll get 5, 5, 5, 6. But just a little remark, which was, oh, wait a minute. So the number of maximal elements stayed the same, but the difference between max and min went down. Difference between max and min went down. Difference between max and min did not go down. And the number of maximal elements did not go down. So something was a bit. Why didn't the number of maximal elements go down? Because I was an idiot, basically. I should have added 1 to the 2 smallest, and I didn't. So let's get rid of all that. And just go back to the calculation. I just made a silly mistake there. So add 1 to the 2 smallest, 4, 4, 4, 5, and so the max minus min has gone down. Now what's going to happen? I'll add 1 to the 2 smallest, but I'll pick those two out of the 2 smallest, so 4, 5, 5, 5. Now, so what I was saying was wrong. The number of maximal elements has gone up. And what's going to happen next? I'll get 5, 5, 5, 6, and I'm into a sort of cycle, which is, of course, was inevitable that that would happen. So let us just think about what's going on here. I think it's going to be something a little bit subtler. So if we do this algorithm, I think it should end up with everything being equal to within 1. That would be my new guess. And that if we carry on, always adding 1 to the smallest things, it's going to be just the number of the change is going to be m mod n or something like that. That looks as though that's what's happening here. So here I've got 3 4s, and then when I add 2 I get 1 4, and then when I add 2 more, add 1 to a couple of things, I now get back to having 3 maximal elements again. Sorry, 3 of the smaller ones. And then when I do it again, I get 1 of the smaller ones, and so on. So that looks as though it's the pattern. So let me think about whether that is going to be. So let's go back to a1 less than or equal to ... less than or equal to an. If I keep adding 1 to the m smallest things, what if I've got, let's just try one more example. I want to know what happens if I've got one rather small one, and let's say 4 much bigger ones, and I'm adding 3 at a time. So then I'll have 2, 9, 9, 10, 10. Then I'll have 3, 10, 10, 10, 10. And after, so the first step, the max minus the min didn't go down, but at the second step it did go down. Let's make it harder for myself. I'm going to add 4 at a time. So 1, 9, 9, 9, 9. So this first time I'll get 1, 9, 10, 10, 10. And the second time I'm going to be in trouble still. So so that's been 2 there. So then I'll have 3, 10, 10, 11, 11. And the next one I'm going to have 4, 11, 11, 11, 12. And then at last 5, 12, 12, 12, 12. Now at last this thing went down from 8. The max minus the min has been 8 for a long time. But now I've finally got through it all and it's gone down to 7. And I think that gives me a clue about what I can do if I want to decrease the difference between the max and the min. So in theory, what I can do is because m is going to be less than n, if it's not less than n, then nothing is very interesting. But if m is less than n, then if I've got the minimum here, a1, and then here over here I've got a2 up to an, I can just add 1 to a1 quite a large number of times until I get a1 plus r. And all I have to do over here is make sure that that's a bit more complicated because a2 may also be right, so let's just say that I've got a r plus 1, that shouldn't be r, equals an. So either m is small enough, it's smaller than or equal to r, in which case I'm absolutely fine, or if m is not small enough, then what I could do is add 1 to all of these numbers here, and add 1 to the smallest, whatever I'm forced to add it to over here. And then I can just keep going, add 1 to all of those, and then add m to a different choice over here, and add add 1 to all of these, and add 1 to a different choice over here. And once I get to the stage where I have at least once for all of these things not added 1, so for each of these ones I've not added 1, then I will have reduced the difference between the maximum and the minimum. And I think that can probably be worked into a proof that maybe not immediately, but after a while I can get the max minus the min to go down. But it would be much nicer actually if I could just simply argue that some other slightly nicer quantity goes down every single time, rather than having to wait for ages for it to go down. And so instead of the maximum minus the minimum, perhaps I could do something like the variance or something like that. Is that likely to happen? We know it's not always going to go down, though. So I'm just going to go think about this one more time. So if the maximum minus the minimum doesn't go down, I want to say, so I had that full statement, if the maximum minus the minimum doesn't go down, then the number of maximal elements goes down. Now, why was that wrong? Because here was the counterexample 4, 4, 4, 5. And then if I add 1 to 2 of them, then I've got 2 new maximal elements. But that could only work. This was a better example, actually. Maybe if I argued that there's definitely something that's going down here. So max minus min goes down the first time, but then the next time the number of maximal elements goes down. The next time the number of maximal elements goes down. And then when max minus min, so when the number of maximal elements goes back up again, that is the point. So that was not a counterexample. So back here, if max minus min does not go down, then So where did I? Okay. Here's where I'm thinking. I'm thinking I had an argument that said either the max minus the min goes down, or the number of maximal elements goes down. That was wrong, but I have a feeling that it's right, except under very special circumstances, and that's what I want to try to understand. So let's go back to this picture. I'm taking longer than I should on this, but I'm sort of comforted by the fact that I've solved most of the question. It's just a matter of sort of really finishing off the rest. And I have that m is greater than r. Under what circumstances? So we get, so if m were not greater than r, then I would get that an minus a1 will decrease when I add 1 to the first m elements. If m is greater than r, then how many maximal elements am I going to end up with now? I used to have n minus r, and I will get m minus r. And m minus r, that was my argument, m minus r is less than n minus r. So why is that argument wrong if we have 4, 4, 4, 5, but that's the case m is less than r. So if m is, okay, so I think I've seen it now. So if m is less than r, it is not it is the case that an minus a1 goes down, but that's not necessarily what we're going to do, because yes, the number of maximal elements can go up. If, say, I add 1 to the first m things, then the number of maximal elements can go up, but I would need a1, or I'd need at least one of these to be a 4 in order to get another 5. So I need at least am to be an minus 1 in order for the number of maximal elements to go up. So if that happens, then the situation I find myself in is that I've still got this 4 now becomes a new a1. So now I've got 4, 5, 5, 5. But what I want to try and work out is if I'd had instead 3, 4, 4, 5, and I add 1 to the first 2, then I get 4, 5, 4, 5. Or even if I'd had, let's say, 2, 4, 4, 5, then I get 3, 5, 4, 5. No, then that's hopeless, because oh no, that has reduced the size of the biggest minus the smallest. So the only way I cannot reduce the biggest minus the smallest. Oh yes, okay. I think I've got there now. So if m is less than r, or less than or equal to r, then when I add 1 to all these, that is going to decrease an minus a1. The only way that it cannot decrease the max minus the min is if we've got something like this: a1 less than or equal to a2 less than or equal to am less than or equal to am plus 1 less than or equal to ar less than ar plus 1 equals up to an. And now we're adding 1 to all these. So the only way it can't decrease the max minus the min is if am plus 1 is still the min, because this is not going to make it be a new maximum. So we must have equality here. And so actually not quite finished. Oh yes, sorry, no, but for the number of maximal elements to go up, we would need these things all to be an minus 1. So that would have to be an minus 1 as well. But anyway, if these things are all an minus 1, then everything differs by 1, which is what I wanted. And otherwise, I haven't covered all cases. So if for example, I had 3, 3, 3, 3, 10, and I'm only allowed to add 3 things at each stage, then that would go to 3, 4, 4, 4, 10. The number of maximal elements has not changed, and the max minus the min hasn't changed. But what has changed in this case is the sum, which, if the number of maximal elements doesn't change, is going to be bounded above. So if I add in that invariant as well, so what I'm going to say then is that if not all equal up to a difference of 1, then max minus min goes down or stays constant, but number of maximal elements goes down, or number of max elements stays the same, as does the maximum, but sum goes up. And we can't have that situation persisting forever, because if, for example, the number of maximal elements stays the same and the max minus the min stays the same, then the sum can't just keep going up forever, because it's bounded above by the max times the number of elements. And so that proves that we get at least to a stage where they're all equal bar 1. And then I think it really is straightforward that if you've got, let's just, without lots of generality, we've got a bunch of zeros and then a bunch of 1s, and we're adding m things to the smallest of those. So if m is smaller than the number of zeros here, then we're going to add m. If m is bigger than the number of zeros, then we'll get 1, 1, 1, 1, 1, a few 2s, and then back to 1s again. And what has happened to the number of maximal elements? It has, so if that was R and that was S, this is now R, M minus R, and S minus M plus R. So the number of maximal elements has gone from S to M minus R, which equals M minus N minus S equals S plus M minus N, which is congruent to S plus M. It's congruent to yes, congruent to S plus M mod n. So as I suspected earlier, but I'm just checking that here, we do just add M mod n to the number of max mod elements each time we increase the R smallest things once we've got to this stage. Whew. So that took a bit of time to sort out, although somehow the outcome was never in doubt. I think I'm going to stop there. Those were two reasonably nice questions, I thought. As I said, I was quite pleased with the first one coming out systematically in that way. Maybe there's a simpler solution that I overlooked, which seems to be happening quite a lot. And there may be a simpler solution to this one as well. But I'm not in these videos aiming to get the absolute simplest. I'm aiming to get the first one that I get, and then maybe afterwards on further reflection, I or others will spot better solutions. Okay, thank you very much.